This is a great chapter that we're working with because not only is it, I mean, I love algebra so much that I could just do it like all day long. So like this is a great, this is great for that. We get some like mechanics of like just, manipulating expressions. And also, Alex, sorry, it's okay. I need to get, also, it's going to be a great lead-in to the next chapter, which is extra awesome, working with complex numbers. So, okay, no groans. Groan on the inside. Okay. All right. So these properties here are ones we've already learned that we know and love. We know that if you are multiplying two exponential expressions with the same base, then you can just add the exponents. We know that if you're dividing and you've got the same base, you get to just subtract the exponents. And we know that if you are raising an exponential expression to a power, you get to multiply the exponents. None of this is particularly new. We spent lots of time practicing this already. We know that you can distribute an exponent over multiplication and division, but what can we not distribute an exponent over?
Addition.
Or?
Subtraction.
Exactly. So do not, let's all keep in mind that these things generally not equal. Like this is one of the cardinal sins of mathematics. Don't do that.
Cardinal sin.
So, we also know that any non-zero base that you raise to the 0 power, that's 1. Does anybody remember why that's true? It's okay if you don't. I'll remind you.
Because that's a lot of 10.
Well,
One is 0.
I wonder if that's the other way around, like if the dependency is the other way around. Like, is it that log of 1 is 0 because anything to the 0 power is 1? You know what I mean? Like, those two facts are compatible. They're totally related to each other. I could convince anybody of this fact by just looking at a simple string of equations. Let's say I take, well, I don't even have to put in a number. Let's say I take, a squared, and I divide it by a squared. What should that always give me? 1, yeah. So we know on the one hand this is equal to 1. On the other hand, if I apply property 2, what is, using the rules of exponents, what does this say we get?
A to the 2 minus 2.
Yeah, a to the 2 minus 2. I can subtract the exponents, and this is a to the 0. So as long as, and this is only true, by the way, of course, if a is not equal to 0. This is one of the reasons why we require a not to be 0, because this fraction that we started with isn't defined if a is 0, because if it were 0, we'd be dividing by 0 here. So as long as your base is not 0, anything to the 0 power is equal to 1. And then here's another familiar fact that if I raise something to a negative power, it just means that we're taking 1 dividing by a to the positive power. Raising something to a negative power does not make it negative, just makes it small, right? So let's do some warm-up exercises. We want to use only positive exponents in our answers. We've done exercises like this before. Well, this will get us nice and warmed up for some more interesting examples. How might we begin a problem like this?
Distribute the exponent on the x squared.
Yeah, right. So we got this parentheses that's being squared here. So we've got x squared, squared, y squared. Now what's going on here with that fraction raised to the negative 2? What can we do with that?
Distribute the negative 2 to the 2 and to the x.
Yeah, so we got 2 to the minus 2 over x to the minus 2. Good thing we don't have any addition or subtraction to ruin our fun here. What's next?
I gotta flip the negative exponents.
Yeah, right. So within this fraction, let's see. Does anybody mind if I go ahead and call this x to the 4th power? Okay. So how should we write this fraction, Sarah?
So it'll be x to the x squared over 2 squared.
Yeah. Yep, exactly. So we just applied that negative exponent principle. Now what?
Put them all together.
Yep. What do we get?
X to the 6y squared over 4.
Yeah, so we have this multiplying the same base. That means here we get to add those exponents. So we have x to the 6th. The y squared, nothing that guy's hanging out with, so we just bring him right over. Over, and 2 squared is equal to 4. It's a nice familiar type of example. We've worked through these before. Want to do another one?
Oh yeah.
Oh yeah. Okay. 5 times x to the 0. What does that equal?
5.
5, because we know this is 5 times 1, or 5. On the other hand, 5x parentheses to the 0 is equal to 1. So, you know, the moral of the story here is make sure you're aware of on what base is each exponent acting. 2x to the minus 1. What? 2 over x. Because that negative 1 exponent is only on the x, not on the 2's. The 2's in the top of that fraction. What about 2x parentheses to the negative 1? 1 over 2x. See, they tried, you know, they try to pull a fast one on us, but we see right through them. We know that we have to be careful about, you know, being aware what base is each exponent being applied to. And actually be careful, because no matter how many times you've done it correctly, if you're working quickly through a problem, I can't tell you how many times I've seen somebody rewrite this as 1 over 2x. Like, it's just like, you know, make yourself slow down a little bit and pay attention to the details. Sometimes addition and subtraction come along to try to ruin our fun. But that's okay. We can handle it. First thing I do is I write a little equal sign, because I know I've got to try to figure out what this is equal to. What's one way to start this? Flip the b. So by that, I think you mean write it as 1 over b, the b to the negative 1? Yeah. Flip the b sounds like vulgar or something. I don't really know, but... So I guess we have a couple of options here, but there is one option I would like to put forth as sort of a natural next step. And that is that we've got some addition of fractions in the parentheses. We know how to do that. Let's go ahead and get a common denominator and add these fractions. Some people want to kind of go straight to like using this negative exponent and doing 1 over that stuff squared. But as soon as you do that, it's just so unsimplified because we got fractions within fractions and the whole thing's a big mess. And we can make progress a little bit more quickly and easily, I think, if we get a common denominator. Of course, that denominator is b. So now we have 2ab plus 1 all over b, and this is being raised to the negative 2 power. Now what?
Now you could distribute the negative 2 to all of 2ab plus 1.
Yeah, like, but it's still in parentheses? Yep, exactly. So, exactly. So we got just distributing the negative 2 power through the fraction. We have 2ab plus 1 in parentheses to the negative 2 divided by b to the negative 2. And what's our next step? Yeah, flip them over. Yeah, so now we've got b squared over 2ab plus 1 squared. And you could choose, I suppose, to FOIL at the bottom, but I think it's kind of simpler to just leave it in a factored form, so I'm going to leave it like this. We have, so notice that our answer is in the form of a fraction, but we don't have fractions inside of fractions. Fractions inside of fractions is definitely not simplified. And if you have negative exponents inside a fraction, that's tantamount to trying to hide fractions within fractions, like camouflaging the fraction with a negative exponent. So notice we have a nice fraction, only positive exponents, no fractions inside fractions. Let's do some more. How do you want to start this one out?
3 times 1 over L.
3 times 1 over L, so I'll write it as 3 over L. How do you want to write this next guy? Ah, yes, and I'm gonna do this just in 2 steps to make sure that if somebody goes and looks over my work that it's clear. But if you did this in one go, like when we get to the next, so we just used the whole what the negative 2 power means, right? And we rewrote it, and then your next move was let's distribute that exponent. I agree completely. So 2 squared is 4. L squared. If you went straight from this to writing it like that, that's okay. It is not considered poorly communicated. Just, be careful. I know, and you've all been witness to it, the fact that I can make mistakes when I do too many steps in my head at once. So, try not to go too fast. Now what?
Find a common denominator.
Yeah, we're subtracting fractions. We know how to do that. That common denominator would be...
4L squared.
Yeah, so this guy needs a 4L on the top and the bottom. Good thing we've spent all that time working with algebraic fractions. So on top we have 12L minus 1. You guys all look so sad. Cheer up, you guys. We've got rational exponents next.